Okay, well, um, okay. My name is Malathy Batumalay, and currently I'm attached to Inti International University, Malaysia. Today I'll be presenting on the topic silver, zinc oxide, and graphene kretschmann plasmonic sensor for bacteria contamination.
Malathi, sorry to interrupt you. Can you put the presentation in slideshow presentation mode, the PPT?
Okay, so that means I won't be able to see others. Anything, you just alert me. Yeah? Thank you. Sorry for that.
Yep.
All right. Okay, can you see in the presentation mode now?
No, put it in the slideshow mode.
Okay, let me 1 minute. Huh?
Yep.
So that means, is it okay?
No.
Still okay. So sorry. Okay. Actually, it is on the presentation mode already.
Can you at the bottom? Are you able to
Yeah,
see
no.
that
Yes, yes, I
70
can.
below
Slideshow, right?
78%? Yes.
Let me try again.
Yep.
Is it okay now?
Yes, Malathi, we can see it.
Okay,
You
thank you
can.
very much.
Uh, I mean, can you detach the small window? Yeah, close it. Yeah.
I just close it. Okay. All right. Okay.
Perfect.
Thank you very
Go
much.
ahead.
Okay. All right. Good afternoon, everyone. I'm Malathy Batumalay. Currently, I'm attached to Inti International University. Today, I'm going to present on the topic silver, zinc oxide, graphene kretschmann plasmonic sensor for bacteria contamination. All right. My topic here is going to cover on the major issues that we are facing today, which is water quality. So we are aware that water quality monitoring plays a major role in safety and also in public health management. So one of the root cause that actually affects the water quality is the amount of bacteria in the water solution. So we came up with the idea where bacteria detection in water solution need to be prevented in order to keep human away from contamination and diseases. So this setup here that we have built is called the kretschmann surface plasmon resonance sensor, which can be used for bacteria detection in water solution. The source that we are using for this kretschmann surface plasma resonance is a sensor with a source of 633 nanometer helium neon laser source, and also we are using a BK7 prism with the angle interrogation to access its visibility. The sensor that we have created was coated with silver, zinc oxide, and graphene, and we have successfully achieved a 70% sensitivity, which have improved over the only silver coated sensor that was used previously. All right. We have done some preliminary studies where we found out in the past there were several researchers who have come out with the idea to use D-shaped and tapered fiber sensor, which was found to be fragile and easily breakable. So, knowing that SPR sensors have good gold, silver, or copper coatings will be able to show good sensitivity. However, there was a small research gap here where gold shows good sensitivity, but there was a wide resonance dip. So that's why my team have selected to use silver, which shows a narrow dips, but it also provide a strong response to analyte. However, with the enhancement using additional coatings, it was needed to protect the sensor layer from oxidization or falling, which means there is some problems that occur due to oxidization. Now, using zinc oxide, it has helped to improve the plasmon response due to its effect on electric field at the dielectric metal interface. At the same time, graphene is also commonly used due to the affinity of biomolecules. Moving forward in our methodology, a sensor for E. coli bacteria in water solution is investigated. The Kretschmann setup using BK7 prism was coated using silver, zinc oxide and graphene to ensure a strong response to the analyte. The proposed sensor was designed using Kretschmann setup as mentioned earlier. We have chosen the wavelength of 633 nanometer and it is provided by the helium-neon laser. The first step was optimizing the prism materials choice. Different prisms such as SF10, BAK1, BAF10, and BK7, which have the refractive indices between the range of 1.723, 1.667, 1.470, and 1.515 was investigated respectively. This is our setup. You can see in the figure below, it shows how the placement of helium-neon laser, which provide the source, and we are using a prism, and at the same time the prism is coated with zinc oxide, graphene and silver material. It acts as a surface for plasmonic resonance, and the output is detected using a light detector. Furthermore, silver was chosen as a metal layer and was tested to find out what is the optimal thickness that is required. We found that silver's refractive index was obtained via Drude model. The zinc oxide layer was analyzed in the thickness between the range of 5 to 25 nanometer. The graphene layers was investigated as G layers at the angle of 0.34 nanometer. And the graphene is called, the G represents the graphene's layer number. E. coli's refractive index is 1.383. The range chosen was for low E. coli concentration, so the maximum tested range was at 1.338. We use a method called transfer matrix method due to multi-layer sensor reflectance, which was sufficiently investigated with minimum approximation. The resonance occur at the angle at which maximum energy transfer occurs. I've also shared the equation provides the resonance angle. Surface plasma resonance SPR occurs when photon energy couples with the metal dielectric interface plasmons. The propagation constants must follow the equation that is given in the diagram below. Okay, this is our results. The first stage of sensors design is choosing a prism type, as I have mentioned earlier, with a suitable response to refractive index change between the range of 1.333 to 1.338 range. The prism tested were BK7, BAF10, BAK1, and SF10. However, we prove here that BK7 provides the best sensitivity at 130-degree angle and at this range of refractive index unit. Follow up the silver thickness effect on the minimum reflectance and sensitivity as shown in the diagram. We observe that the 50 nanometer layer achieved the lowest reflectance and reached the closest to the critical coupling. The sensitivity of the 50 nanometer layer was also the strongest at 130-degree refractive index unit. The 35 to 45 nanometer layer shows increasing reflectance with decreasing thickness. The smaller thickness achieves inefficient coupling, causing higher reflectance since less light energy is coupled to the plasmons. The figure below represents the zinc oxide thickness selection. We observe that the 15 nanometer layer shows a sensitivity of 200 degree per refractive index unit. The sensitivity improved in the range of 5 to 15 nanometer and then dropped beyond that point. Therefore, the thickness of zinc oxide layer results in expanding the metal dielectric interface. Thus, the distance between the energy coupling region and the analyte is wider. The energy material interacts becomes weaker with limiting sensitivity. The figure below summarizes the graphene layer's effect on the sensor response. As we are aware, graphene layers can improve the sensor's response to analyte due to the graphene's effect on electric field in material variation region. We observe the sensitivity reaches a 220 degree per refractive index unit response with single graphene layer. The sensitivity lowers with more graphene layers until it reaches 11 at 80 degree per refractive index unit. The sensitivity is lower with increasing layers because the interaction becomes thicker, limiting the analyte's effect on the light plasmon coupling. Now, let's look at the figure which summarizes the bacteria contamination sensor. It presents that the silver layer responds to the analyte. The angle shift results in a 50 nanometer layer reaching up to 130 degree per reflective index unit. The 15 nanometer zinc oxide effects, which causes 200 degree per reflective index response. Figure C at the bottom shows how the graphene layer causes the sensitivity to reach 220 degree per reflective index unit. At the same time, the figure that you can observe here presents that the electric field at the coating and the BK7 prism. The BK7 prism coated with 50 nanometer silver, 15 nanometer zinc oxide and a graphene layer shows the penetration depth of the field. The distance reaches almost 400 nanometer beyond the graphene coating layer. The penetration depth gives an assessment of the analyte's effect on the plasmonic response. As for the conclusion, a Kretschmann's SPR resonance sensor is presented in this paper. The sensor can provide real-time detection of bacteria contamination. With the power source of helium-neon laser source, it provides 633 nanometer of incident light. The prism choice, silver thickness, zinc oxide thickness, and graphene layer is successfully investigated. The selected parameters were a BK4 prism, 50 nanometer silver, 50 nanometer zinc oxide, and a layer graphene. The sensitivity reached was 220 degree per refractive index units. This sensor can assist in monitoring water source for safety. With this, we are able to prove that the bacteria contamination which appears and found in lower intestine which can cause sickness and watery diarrhea can be prevented, because at the end we are able to test and validate that the water is safe for human to use. The silver was actually prepared using Drude model, as I mentioned just now, which described the electrical conduction in metals by treating the free electron as an ideal gas of particles which is moving among the fixed positive ion. The presence of zinc oxide is able to enhance the
Hi, Malathy.
plasmonic field interaction, and at the same time, with the
Hi,
help
Malathy.
of graphene, it helps to improve bimolecule affinity. Yes, sir.
Uh, you have stopped sharing your screen. Can you please share
Okay,
it?
sure. Yeah, sure. Done. Okay, sir. Sorry, sir. Actually,
No,
that
we cannot
was no, that
see your
was my
screen.
last slide just now on the conclusion.
Okay, you stopped sharing the screen?
Yeah, I stopped sharing.
Okay, fine. Yep.
Okay, all right. So I just want to conclude here that we are able to come out with an investigation for E. coli bacteria, which is found in lower intestine, which cause sickness and lead to watery diarrhea. We were using silver, which was prepared using Drude model, as I mentioned earlier, which described the electrical conduction in metals by treating free electron as the ideal gas of particles, which is moving among the fixed positive ion. With the use of zinc oxide, it helps to enhance plasmonic field interaction, and graphene have helped to improvise the bimolecule affinity. The method that we use is TMM, which is a transfer matrix method to model the reflectance and determine the resonance angle. With that, I conclude my presentation. Thank you.
Thank you, Malathi, for your wonderful presentation. In fact, it was very thoughtful and insightful for all the participants. Any questions from the audience? They can raise their hand or give any reaction so that we can bring them onto the floor. Any questions from the team so that we can bring them onto the floor regarding the questions to the presenter? They can drop a message or raise a hand so that we can bring them onto the floor. Okay. I see no more questions. Thank you so much, Malathy, again for your wonderful participation. We keep on seeing you in our conferences and delivering value content to all the participants. That is really commendable from your end. And I'll inform all the participants that Malathy would be the moderator for this conference going forward.